Hi everybody, this is Nifish. In today's lecture, we are going to go over and run the 2D FFT, okay, two-dimensional fast Fourier transform on an image and convert the image to the spatial frequency domain, okay. And why we are doing this FFT? There are many reasons, but one of the reasons is image filtering and noise removal, okay. And I'm going to show that after you convert that image to the frequency domain, okay. And then once we are done filtering that image, okay, going to convert it back to the spatial domain using the IFFT2, okay, which is the inverse fast Fourier transform. 2 denotes to the 2 dimension, okay. So first of all, we have to import numpy as np and matplotlib.pyplot as plt. So this is for plotting purpose, and numpy, we are going to get the two-dimensional FFT function from numpy, okay. So let's import our image. So for that we can do plt dot I am read. So we are reading the image, and I have an image already saved. So that is pigeonjaw.jpg, and going to store that image in a variable called img, okay. And now let's visualize that image. So plt.im, and then you press tab and you will see the options. So I'm show, and then name of that image is img, right? Name of the variable where we have stored that image. So let's run it. Okay, so this is our image, okay, and we are going to work on this image. We are going to apply the 2D FFT on this image and going to convert it into frequency domain, okay. And then we are going to use both high pass and low pass filtering, and going to convert back to the original spatial domain, okay. So first let's find out one thing, which is the shape of the image, okay. So img.shape, if you press that, so this is a color image, right? So basically we have let me write it down here. We have 674 rows, okay. Then how many columns we have? We have 1200 columns, and we have three channels, which is R, G, and B: red, green, and blue, right? So these three color channels is basically giving the color appearance, okay. And this row and column, they have the intensity values. So this is, we can also call pixels, okay. And they have some values inside every row and column, and that is basically the intensity. So in 1D FFT, let me explain one thing. 1D FFT, we call the frequency is samples per second, right? So how many samples we are getting per second, that is basically the frequency, right? And in 2D, we'll just say it is intensity, okay, per pixel. So basically you see we have row and columns, and they are representing the intensity values, right? So basically how much is the change of the intensity per pixel, and that is going to give us the spatial frequency, is going to give us that information, okay. So one thing is clear, we do not need these three channels, okay. Okay, we just need the row and column which has the intensity value. So we have to get rid of these three channels, RGB. Basically we have to convert this image to the gray image, okay. And in gray image we have only row and column values with the intensities. We do not have these color dependencies, right? So let's convert this image to gray image. So image gray, and then we have that image. Let's separate the red, green, and blue. So img, then uh, this is the red channel. So basically all rows, all columns, and then the first channel is 0, that is the red, right? So in similar way I have to write down two more for green and the blue, right? So green is 1 and blue is 2, okay. So Uh, so if we want to get rid of this color, these channel dependencies, we can add all these three and divide by 3, right? Basically the averaging of the color. However, the more standard formula is multiply this with some factors. So for the red color, you multiply it by 3, and for green, you multiply by 6, okay, and for blue, you multiply by 0.11, okay. And these values, basically this is well derived, you can find it in Google, okay. And this is kind of like human perception average, okay. So basically we'll just see the gray image if we multiply by these values, okay. And let's visualize that image. So plt dot I am show, okay, and then we are going to visualize this image gray, and we have to put it in a color map. C map is gray, okay. So let's run it, and this is our gray image, okay. So here we can also find out the shape, and you will see we do not have any channels here anymore. Oops, this is all caps. So shape, so you see we have only row and column values. We do not have RGB channels, okay. And let's run it as well. So you see all these values here, okay. These values, this is what is I'm calling the intensity values. So this is each pixel, and they have some intensity values, okay. So we have our grayscale image, and we are ready to run the FFT, okay. So what we need to do is np dot, we're calling that FFT library, right? So np.fft, then FFT2. 2 means two dimensional, okay. And then we have this gray, and we are putting it in a variable called ft, okay. Let's run it. So it went through, there is no issue, okay. And after running that FFT, we have to do a FFT shift. So for that, FT dot, I'm going to tell you why we are doing the shift. So FT shift is np dot FFT, again calling the FFT library, and then inside that FFT you will have that FFT2. So this is one dimensional, this is two dimensional, okay. And then you have this FT, right there, and this is going to be, sorry, this is going to be FFT shift, because we already have done the FFT, right? So this is FFT shift, okay. And then let's plot the image, okay. So plt I'm show, okay. And to plot that, we have to plot the magnitude, okay. So 20 times log np.log, okay. And then we have np dot absolute value, because when we do the FFT there are complex numbers, so we just need to take the absolute value and then FFT shift, okay. So and then at last I think we have to put down that color map, which is gray, okay. Let's run it. Okay, so this is our spatial frequency, okay. So before getting into that, this image, just going to say one thing, why we are running the FFT shift, okay. So if we do the FFT 2D FFT of this image, the low frequency components will be starting in the left, okay, right here, but we want to have everything centered, right? So we want to have all the low frequency components in the center, and if we move, and once we move to the sides, it's going to be the high frequency components, right? The value is going to increase. So we want to have the low frequencies centered, and that is why we are using this FFT shift, okay. Now one will say, what is the reasoning of converting this image to the frequency domain? As I mentioned, we can do some filtering operations easily in Fourier domain, right? So first filtering operation is like, since I mentioned like all the low frequency components are centered, we can use a high pass filter or a low pass filter. So basically, if we want to eliminate the low frequency components in the center or the high frequency component on the sides, we can do that. Okay, and the operation is easy here. Okay, and then we can convert the image back to the spatial domain. Okay, so to so I mentioned like two types of filtering, right? So first use the low pass filtering. Okay, so for the low pass filter, we will only pass the low frequency components, right? So basically right here. Okay, so let's create a mask. Okay, so first of all um, we need to find out the shape again. So image gray, and then we have the shape, right? And this parameter gives two outputs, right? One is the row and the other is the column. Okay, so having those values stored in row and column variables right here. Okay, and then we need to find the center, right? So if we divide the number of row and column, then we'll just be in the center. And you can also see the subject is lying kind of in the center, right? And the background informations are mostly the high frequency components or noises, and the subject is kind of in the center. Okay, so we have this, and then we have to find the middle, and for that, so we can do the center row. Okay, which is row divided by 2, and then center column is column divided by 2, two black slashes, because we do not want any float number. Okay, and then run it, and there is no error. And then let's create the mask. So basically we want, let's say, C row, so we want, let's say, 20 pixels center to the left and center to the right. So 20 center row to the left and to the to the right. So 0 plus 20, so we're going to get 40 pixels, right? And then we gotta have these columns, which is column, C column, and then let's say also 20 in the column direction as well. So let's say 20, then C call, so 20. Okay, and going to get this like this square kind of masking or the numbers from this shifted version right here, FT shift. Okay, so basically that image what we have, we're just going to focusing on the center or the low frequency components. Okay, and then FT LPF, let's say the variable name LPF is equals to this guy. So basically from the values of frequency transformed shifted numbers, we are just focusing or getting 40 pixels. You can see there, right? 40 on the row side and 40 on the column, right? And then let's run it. There is no error. And then the next step is going to convert this. So this is still in frequency domain, right? So let's convert that into the image. Okay, like so the spatial domain. So FT LPF, and for that first we have to do the shifting. Okay, so np dot FFT dot FFT shift. Okay, so we are shifting again. Okay, and putting it into a variable called FT LPF shift. Okay, and after we do that, we are ready to apply the I52. Okay, so exact same variable. Okay, let's say I52. Okay, and then np, calling the np library, from there FFT, then I52, which is two-dimensional. Okay, and the input is the shifted version right here. Okay, filtered and shifted version. So do that, and then we have the, this is in the image domain, right? Like the spatial domain. So we can visualize it. So plt dot I'm show, okay, and the input is this guy right here, okay. So this guy, and since we are running I52 is going to be a complex number, so for that we can do np dot real of this guy, okay, and we have to again have the color mapping. So cmap is equals to gray, okay. So let's run it. Okay, it doesn't look promising, so probably, okay, so I think I have made a mistake here. It has to be a plus sign right here rather than a colon. Okay, and if we compile and run it, we'll get that image, the low pass filtered image. Okay, this image is blurry and it's really hard to understand what's there. So I'm just taking some more pixels. So 30 here, 30 there, and then for in the column as well, 30 and 30. So it's going to be 30 pixel times 30 pixel. Okay, and then compile everything. Okay, so this is our original image right here, and this is the low pass filtered image. So you can see, like, we are, rather than having 600 times 1200 image, we are having a much more shrinked image, but it's still like the subject is there. You can understand the subject, but the background is smoothed out. It's kind of I would say like all the high frequency components, which describes the edges and boundaries, kind of filtered out. Okay, so I have done the high frequency filtering here as well. So basically here, if you look into the line, I just wrote the code just to save some time, but here you can see like I'm just making 0. Okay, and just taking the high frequency components right here, doing the same I50 shift and then I52. Okay, but this is the line where I'm doing that. I'm filtering out the low frequency component, and you can see I'm just getting the edges and contours of that image. Okay, so this is the benefit here. If you do all these calculations in Fourier domain, it's much more easy, okay, to do this in spatial frequency domain and then convert the image back to the spatial domain, right? So two advantages. Okay, in the low pass filtered image, you can see it's kind of blurry, but you can see the subject and it's shrinked. You will lose some resolution, but you will have a much more smaller image with still conveying the same kind of information, right? And in the high pass filtered image, you can see the edges and boundaries, all these things. So basically this will be important, when you are trying to detect a face or some boundaries, okay, some contours. And since it's high frequency, you can see, like, the changes of intensity is higher, right? Okay, so intensity per pixel is higher, and that's why this image is just showing the shapes and contours. Okay, I hope you guys learned something from this lecture. Hope you enjoyed it.